Welcome back to CS Connect series. In this video, we are going to discuss about sequences. Sequence is also a mathematical structure, we can say. So after functions, we are into sequences. What is actually a sequence? Let's see some examples now. 1, 2, 3, 5, 8. This is a sequence with 5 terms. Do you find any pattern among these 5 terms? Yes, when you add 1 and 2 you get 3, when you add 2 and 3 you get 5, when you add 3 and 5 you get 8. Similarly, we'll see another sequence 1, 3, 9, 27, 81, it goes on and you have something called 3 power n. So whenever you substitute a value for n, you get this sequence. When n is equal to 0, you have 3 power 0 which is equal to 1. When n is equal to 1, it is 3 power 1. When n is equal to 2, it is 3 power 2. When n is equal to 3, it is 3 power 3. And here you can find this goes on. So this is an infinite sequence. It means you don't know what's the end. You don't know how many elements are totally present. But this 3 power n is actually coming along the series and it is not the end of the series. So what are these actually? They are all sequences. A sequence is a discrete structure that is used to represent an ordered list. Why have they specified it to be ordered? It's because we have the value n is equal to 0, 1, 2, 3, etc. in this particular case. When n is equal to 0, you have the appropriate value 1 here. When n is equal to 1, you have the appropriate value 3 here. So this goes in a ordered way. Whenever n has a particular value, based on that particular value, this particular 1, 3, 9, 27 terms will be computed. So this is like something like a function. So you are computing using a particular value and finding another value. This is a function, but it gives elements in an ordered list is what they say. Now let's get into the formal definition. A sequence is a function from a subset of the set of integers. You can take the set to be either 0, 1, 2 or from 1, 2, 3. So based on the context, it will start from 0 or it will start from 1 to a set S. So just read this. A sequence is a function from a subset of integers to a set S. The notation A subscript n is used to denote the image of the integer n. So if we have n to be the domain, then an will be the codomain value. An is a term or an individual term of the sequence. The notation set with element an is used to describe the sequence. The list of the terms of this sequence will be a1, a2, a3, a4. So whenever you want to describe a sequence, you use this particular notation. A geometric progression is a sequence of the form a into r, a into r square. So if you go to number system playlist, you can find a video called base of a number. When you had a number called 7239, we said this can be represented as 7 into 10 to the power 3 plus 2 into 10 to the power 2 plus 3 into 10 to the power 1 plus 9 into 10 to the power 0. So this 10 is what we defined as base. Here we can equate the same thing, but here the r term will be called as the common ratio and the initial term is given by a. So why is only a considered here? If you have r power 0, this will be a into r power 0 which is equal to a. Then you have r power 1, r power 2 up to r power n. You keep multiplying a along with the common ratio. So this common ratio and the initial term both are actually real numbers is what they say. This is geometric progression. A geometric progression is a discrete analog of the exponential function f of x is equal to a into r power x. So based on the value of x, the sequence will have the terms. Let's take an example. The sequence is bn with b subscript n is equal to minus 1 the whole power n. So how will we get the list of terms for this particular sequence? From 0 we have to start. So it is b0, b1, b2, b3 and b4. When the value of n is equal to 0, you have minus 1 to the power 0 will be 1. When you have minus 1 to the power 1, it is minus 1. When you have minus 1 to the power 2, this will become 1. When it is minus 1 to the power 3, this will become minus 1. So whenever you have even terms, you end up with 1. When you have odd terms for n, you end up with minus 1. So this is an alternate sequence of 1 minus 1, 1 minus 1, and it keeps on going. So this is what they have mentioned. They have given the first 5 terms. So the first 5 values are alone indicated for this particular sequence. Next, let's see about arithmetic progression. An arithmetic progression is a sequence of the form a plus d, a plus 2d. It goes on till a plus nd and it moves on, where the initial term a and the common difference d are real numbers. Here it is the common ratio and here it is the common difference. It's because when you take a plus d minus a, when you subtract these two terms, you ultimately get d to be the difference. Again go for third term and the second term. A and minus a will get cancelled. 2d minus d will be d. So the difference between two terms at a time will be this particular common difference d. Here if you take, it is the same case for geometric progression. A r divided by a will give you r only. A r square divided by a r will again give you only r. So this is the common ratio they are talking about in geometric progression, and here this is the difference d that they are talking about in arithmetic progression. And arithmetic progression is a discrete analog of the linear function. So this is exponential function and this is linear function. F of x is equal to d into x plus a. Let's take an example. The sequence is Sn with Sn is equal to minus 1 plus 4n is given by. The list of terms is taken as S0, S1, S2 and S3. So let's compute for n is equal to 0. Minus 1 plus 4 into 0. This will give you minus 1 plus 0 which is equal to minus 1. When n is equal to 1, you have minus 1 plus 4 into 1 will give you 4. This will give you 3. When n is equal to 2, minus 1 plus 4 into 2 is 8. This will give you 7. When n is equal to 3, minus 1 plus 4 into 3 will give you 12. This is equal to 11. So for the first 4 terms, they have given 4 values here in the sequence. So this is how we will be computing. Actually what we are doing here, we are actually supplying values to a particular function and we are finding the subsequent terms in the sequence. Now where does this particular concept come in the connect? The max CS connect. Sequences of the form A1, A2 to AN are often used in computer science. These finite sequences are also called as strings. The string is denoted by A1, A2 up to AN. The length of the string is the number of terms in the string. The empty string denoted by lambda is the string that has no terms. Let's take an example of the string ABCD. So what is the length of the string? You have to count the individual terms here. It is ABCD. So there are 4 characters in this string. So whenever we say string in programming context or in system context, it is just the concatenation of individual characters we will say. It's just the joining of individual characters. In that aspect we can take. Now we are going into a very prominent topic called recurrence relation. Recurrence relation concept is a part of sequence topic, but this recurrence relation is a very detailed concept that we will be discussing later in this series. As for now, we will just understand what is recurrence relation. Another way to specify a sequence is to provide one or more initial terms together with a rule for determining subsequent terms from those that precede them. Instead of just giving a particular expression and asking us to calculate, here they will be providing one or more initial terms. They will give a rule. It will make use of the initial terms to calculate the subsequent terms. One example that should come to your mind immediately will be Fibonacci series. So when you take Fibonacci series, you will have 0, 1, 1, 2, 3, 5, 8, it goes on. So how will we actually calculate? Initially you can fix 0 and 1 as the initial terms. This is the first term, second term and this is the third term. You have to calculate the third term from the sum of first and second term is what? we give as the rule. A recurrence relation for the sequence an is an equation that expresses an in terms of one or more of the previous terms of the sequence, namely a0, a1 up to an minus 1 for all integers n with n greater than or equal to n0, where n0 is a non-negative integer. So if you want to calculate this to be a0, a1, a2, in order to calculate a2 you need a0 and a1. In order to calculate a3 you will need a1 and a2. So we are just computing the previous two terms. That's what they say. It will be expressed in the form of one or more of the previous terms of the sequence. A sequence is called a solution of a recurrence relation if its terms satisfy the recurrence relation. Sometimes they will give a sequence in the form of this particular notation and they will ask you whether it is satisfying some kind of recurrence relation. If it satisfies the recurrence relation, then we can term that particular sequence as the solution of that recurrence relation. A recurrence relation is said to recursively define a sequence. Recursively means repeatedly you are using it to compute something. Let an be a sequence that satisfy the recurrence relation. An is equal to an minus 1 plus 3. A0 is given as 2. What are the values of A1, A2 and A3? So they are asking for 3 values. A1 is given by an minus 1. So it is a1 minus 1 which is equal to a0. a0 plus 3. What is the value of a0? 2. 2 plus 3 will give you 5. So the first number will be 5 here. Then we have a2. a2 will be a2 minus 1 which is equal to a1. a1 plus 3 will give, already we have computed it as 5. 5 plus 3 will give you 8. So the next number will be 8. What about a3? a2 plus 3. So again we have a3 minus 1 which is equal to a2. a2 plus 3 is 8 plus 3 which is equal to 11. So we have 3 terms for a1, a2, a3 here. So this a0 is equal to 2 will be called as the initial condition. So this is what they have mentioned as initial terms here. The initial conditions specify the terms that precede the first term where the recurrence relation takes effect. So here the first term will be a1. But how are they asking us to calculate this a1? Based on the previous term. So this previous term will be termed as the initial condition or the initial term with which you are going to work towards the recurrence relation. Now we will get on to the famous Fibonacci sequence example. The Fibonacci sequence f0, f1, f2 is defined by the initial conditions f0 is equal to 0, f1 is equal to 1. And the recurrence relation fn is equal to fn minus 1 plus fn minus 2 for n is equal to 2, 3, 4. Why are we starting n with 2? Because f0 and f1 are already given as initial condition. So what should be the next term? It should be f2, and moreover when you substitute f2 here, 2 minus 1 will give f1, 2 minus 2 will give f0. Only with f1 and f0 you are going to compute f2. The recurrence relation for the Fibonacci sequence tells to find successive terms by adding the previous two terms. So let's take f2. This is fn minus 1 plus fn minus 2. 2 minus 1 will give 1, 2 minus 2 will give 0. f1 plus f0 is 1 plus 0 which is equal to 1. So we have f2 is equal to 1. Now fn minus 1 is 3 minus 1 which is equal to 2. And 3 minus 2 is 1 here. So f2 plus f1, this one along with this one will give you 2. f3 is 2. What about f4? n minus 1 is 4 minus 1 which is equal to 3. 4 minus 2 is equal to 2. So f3 plus f2, these two together, 2 plus 1 will give you 3. What about f5? f4 plus f3. So this is 5 minus 1 which is equal to 4 and 5 minus 2 which is equal to 3. So here f4 is 3 and f3 is 2. 3 plus 2 will give you 5. So we have F5 is equal to 5. What about F6? 6 minus 1 is 5, 6 minus 2 is 4. F5 plus F4 will give you 5 plus 3 which is equal to 8. So this is how we will be subsequently calculating using this recurrence relation. Suppose that an is the sequence of integers defined by an is equal to n factorial. When you have 5 factorial, this can be expanded as 5 into 4 into 3 into 2 into 1. So now just apply to n factorial, n into n minus 1 into n minus 2 into up to 1 it has to go. So you are computing with the previous terms is what I am trying to say here. The value of the factorial function at the integer n where n is equal to 1, 2, 3. N factorial is given by n into n minus 1 factorial is what they say. So this 5 factorial can be represented as 5 into 4 factorial. What is 4 factorial? 4 into 3 into 2 into 1. Do we get this sequence completely here? Yes. So this can be expressed as n factorial is equal to n into n minus 1 factorial. This n minus 1 factorial expansion is what they have given inside the brackets as n minus 1 into n minus 2 into up to 1. So this can be expressed as n into this n minus 1 factorial can be treated as the previous term of the sequence. So this is a n minus 1. So let's substitute. When n is equal to 1, this will be 1 into a0. So let's take a0 to be 1. So this will be 1. When we take n is equal to 2, it is 2 into a2 minus 1 which is a1. So we have the value of a1 to be 1. So 2 into 1 will be 2. Then we have n is equal to 3. So this is 3 into a2. What is a2? We know it is 2. So 3 into 2 will give you 6. What about n is equal to 4? This will be 4 into a3. What is a3? It is 6. So it is 4 into 6 which is equal to 24. Now just compute 4 factorial alone. We have 4 into 3 into 2 into 1. This is 12. 12 into 2 will give you 24. So initially we are calculating 1 into 2. Then we are calculating 3 into 2. Then we are calculating 4 into 6 which will give you 24. Now go for n is equal to 5. 5 into a4 will give 5 into 24 which is equal to 120. This is how we are calculating n factorial. Since I took the example as 5 factorial, I expanded till 5. The sequence of the factorials satisfies the recurrence relation an is equal to n into an minus 1 together with the initial condition a1 is equal to 1. They have given the initial condition as a1 is equal to 1. So from n is equal to 2, you have to calculate this particular part. The recurrence relation together with the initial condition. When you have an is equal to n into an minus 1 and the initial condition a1 is equal to 1. This recurrence relation along with the initial condition is called a closed formula for the terms of the sequence. They are together called as the closed formula. So next time when there is a problem where they ask for closed formula, it means based on the sequence you have to find a recurrence relation and an initial condition for that relation to be computed. Now we will get on to the term called iterations. Let an be a sequence that satisfies the recurrence relation an is equal to an minus 1 plus 3. This particular example we have already seen for n is equal to 1, 2, 3. Solve the recurrence relation and initial condition. We can successively apply the recurrence relation starting with the initial condition a1 is equal to 2. So when you have a2 is equal to a2 minus 1 plus 3, this will be a1 plus 3. So to start with, you are given the initial condition a1 is equal to 2. And working upward until we reach an to deduce a closed formula for this sequence. Let's take a2. a2 means we have to go with a1 plus 3. So what is a1 plus 3? It is 2 plus 3. They have given the initial condition here. When you go to a3, it is a2 plus 3. So this is a2 this is plus 3. How are we actually representing this? We are representing this as 2 plus 3 into 2. So just add them, you will have 2 plus 6. You can represent this as 2 plus 3 into 2. That's how they are represented here. Let's go to A4. You have to take A3 plus 3. Now take this to be A3 and then along with that you are having another 3. Now this 3 is getting added here. So this will become 3 into 3. Then you have AN which is equal to AN minus 1 plus 3. Here you have A4, but how many times are you multiplying this 3? You are multiplying it 3 times. So when you have AN minus 1 here, how many times you should actually multiply? This one should be multiplied for n minus 2 times. We are going to find AN. So we have to multiply 3 till n minus 1 times. So this is given by 2 plus 3 into n minus 1. So we are working upward until we reach AN to deduce a closed formula for the sequence. We can successively apply the recurrence relation starting with the term AN and working downward until we reach the initial condition A1 is equal to 2 to deduce this same formula. So what they are saying in the first place is we are starting with the initial condition and moving towards AN. That is what we did here. Now here we are starting with AN and we have to go till A1 is equal to 2. This is what we are going to do here. So AN is given by AN minus 1 plus 3. So what is AN minus 1? It is AN minus 2 plus 3. So this particular part is AN minus 1. Now we know this is in the form of AN minus 2 plus 6. How can 6 be represented? It can be taken as 3 into 2. So whatever subscript you have here, this subscript number is what is repeating here for 3. Now let's go for AN minus 3 plus 3. This is for AN minus 2. This will become AN minus 3 plus 3 into 3. So if you go this way, you will have A2 plus 3 into n minus 2. So we know A2 can be expressed as A1 plus 3. So this particular expression is what we are placing instead of A2. This plus 3n minus 2 will stay as it is. Now this can be solved as A1 plus 3 plus 3 into n minus 2. This will be 3 plus 3n minus 6. This 3 will be computed along with the minus 6 and you will have 3n minus 3. Now take 3 outside, this will become n minus 1. So this A1 term is what we are equating it to 2. This sequence is nothing but an arithmetic progression is what they say. What is actually iteration technique? The recurrence relation is iterated or repeatedly used. This kind of working from A1 to AN is called as forward substitution. Successive terms beginning with the initial condition and ending with AN. You go in this particular order. That is what they call as forward substitution. Then what about the second technique? It is called as backward substitution. We are starting with the final term and moving towards the initial term. Starts with AN and iterated in terms of falling terms of the sequence until A1. Now we will learn about some special integer sequences. When trying to deduce a possible formula, recurrence relation or some other type of rule for the terms of a sequence, when given the initial terms, try to find a pattern in these terms. So let's take an example. How can we produce the terms of a sequence if the first 10 terms are 5, 11, 17, 23, 29, 35, 41, 47, 53 and 59. What is the pattern that you can find? 5 plus 6 will give you 11, 11 plus 6 will give you 17, 17 plus 6 will give you 23, 23 plus 6 will give you 29, 29 plus 6 will give you 35, 35 plus 6 will give you 41, 41 plus 6 will give 47, 47 plus 6 will give 53, 53 plus 6 will give 59. So you are adding 6 to every other term starting with 5. Each of the first 10 terms of the sequence after the first is obtained by adding 6 to the previous term. From here we are adding 6. Consequently, the nth term could be produced by starting with 5 and adding 6 a total of n minus 1 times. So how many times they have added 6? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times they have added. So 9 into 6 will give 54. Along with 54, you have to add 5. Then you will get 59. That is what they say. You have to add 6 for n minus 1 times in order to find the nth term. Therefore, the nth term is given by 5 plus 6 into n minus 1. So, just solve this. 5 plus 6 into n minus 1 will be 5 plus 6 into n minus 6 into 1, which is 6. Then we have 6n here. 5 minus 6 will be minus 1. So, we are getting 6n minus 1. Just start with n is equal to 1. 6 into 1 minus 1 will give 6 minus 1, which is equal to 5. What is 6 into 2? It is 12. 12 minus 1 will give you 11. 6 into 3 is 18. 18 minus 1 will give you 17, and this goes on. This is an arithmetic progression where A is equal to 5 and D is equal to 6. Just check. This is A. Then we have A plus D, which is equal to 11. Then we have A plus 2D. So this is 5 plus 2 into 6, it is 12. This will give you 17. So it goes on. So this is definitely an arithmetic progression with A is equal to 5 and D is equal to 6. When the common difference concept comes in, we can equate it to arithmetic progression. Now let's see another example. Find formulae for the sequences with the following first 5 terms. 1, 1 by 2, 1 by 4, 1 by 8, 1 by 16. Actually, this is in the form of 2 power 1, 2 power 2, 2 power 3, 2 power 4 under fractions. The denominators are powers of 2. The sequence with an is equal to 1 divided by 2 power n, where n is equal to 0, 1, 2. So, this can be taken as 1 divided by 2 power n. So, when n is equal to 0, we have 2 power 0, which is equal to 1. So, 1 by 1 will give you 1. Then, when you have n is equal to 1, it is 2 power 1. When n is equal to 2, it is 2 power 2. So, you have 1 by 2 power 1, which is equal to 1 by 2. 1 by 2 power 2, which is equal to 1 by 4, and it goes on correctly. This sequence is a geometric progression. So, what is the value of A? We have 1. And what is the value of R? It is 1 by 2. So, whenever you take two terms and divide them, 1 by 4 divided by 1 by 2 will give 1 by 4 into 2 by 1. Altogether, you have 1 by 2 as the common ratio. So, let's take the geometric series. It is AR square. So, here A it is 1. What is A into R? 1 into 1 by 2, it is 1 by 2. What is R square? 1 by 2 the whole square is 1 by 4. 1 into 1 by 4 will give you 1 by 4, and this goes on. So, this is the geometric progression with A value and common ratio value. So, some integer sequences are already computed and given. So, let's see some of those useful sequences. Let's take the nth term and the first 10 terms. When we have n square, what are the first 10 terms? Go for n is equal to 1 to 10. 1, 2 square is 4, 3 square is 9, 4 square is 16, till 10 square we are computing. When it is n cube, 1, 8, 27. So, this is for 1, 2, 3 and everything should be applied cube here. What about n power 4? 2 power 4 is 60, 3 power 4 is 81, 4 power 4 is 256, 5 power 4 is 625. What about 2 power n? 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, 2 power 4 is 16, and it goes on. What is 3 power n? 3 power 1 is 3, 3 power 2 is 9, 3 power 3 is 27, and it goes on. What about n factorial? 1 factorial is 1, 2 factorial is 1 into 2, 3 factorial is 1 into 2 into 3, 4 factorial is 1 into 2 into 3 into 4. Or the other way is 4 into 3 into 2 into 1. Somehow when you multiply you will get 24. Then for 5 factorial we have 120 and it goes on. This is 1, 2, 3, 4, 5, 6, 7. Just compute with the previous factorial. 5 into 24 will give 120. 120 into 6 will give 720. In recurrence relation, this is what we saw as n into an minus 1. Then we have Fn series. This is the Fibonacci series. 1, 1, 2, 3, 5, 8. 1 plus 1 is 2, 2 plus 1 is 3. There is also a sequence called Lucas sequence. Ln is equal to Ln minus 1 plus Ln minus 2 with initial condition L1 is equal to 1, L2 is equal to 3. Since they have given L1 is equal to 1 and L2 is equal to 3, we will start with L3. This is equal to L3 minus 1 plus L3 minus 2. So this will be L2 plus L1. So this is 3 plus 1 which is equal to 4. So the sequence will be 1, 3 and then 4. Then go for L4. It is L3 plus L2. So 4 plus 3 which is equal to 7. Then we have L5. L4 plus L3. This will be 7 plus 4 which is equal to 11. The sequence of terms are 1, 3, 4, 7, 11, 18, 29, 47 and it goes on. They have given only the first 10 terms. Actually, this is similar to Fibonacci series. The only change here is the initial conditions are different. This is the same recurrence relation as the Fibonacci sequence but with different initial conditions. So when you are presented these initial conditions, they are called as Lucas sequence, but it follows the same recurrence relation as that of Fibonacci series. So these are the general sequences that have been already computed with the first 10 terms. Now we are getting into the practice problem session. List the first 10 terms of each of these sequences. The sequence whose nth term is the number of bits in the binary expansion of number n. So when you have binary number 0, it can be represented as 0. When you have 1 in decimal, you have to represent in binary as 1. What about 2 in decimal? You have to represent it as 1 0. 3 will be 1 1. 4 will be 1 0 0. 5 will be 1 0 1. 6 will be 1 1 0. 7 will be 1 1 1. What about 8? You will need 4 bits here. Whose nth term is the number of bits in the binary expansion of number n. So till 1 you need only 1 bit. For 2, 3 you need 2 bits. For 4, 5, 6, 7 you need 3 bits. From 8 you will need 4 bits. So this sequence should contain only the number of bits in the binary expansion. For n is equal to 1. The binary expansion is 1, which has 1 bit. So the first term of the sequence is 1. So let's have 1 here. When n is equal to 2, what is the binary expansion? We have 1 0. This has 2 bits. So the second term of the sequence is 2. You have to just go with the number of bits. When n is equal to 3. That will be 1 1. So again you will have 2 in the sequence. When n is equal to 4, you will have 1 0 0. It is of 3 bits, so you will go with 3. So this is 8, this is 9 and this is 10. If you are not sure about this binary values, I would suggest you to watch number system playlist video in this channel to get an idea about decimal, binary, octal and hexadecimal number systems. So there are 3 bits for 5, there are 3 bits for 6, 3 bits for 7. For 8, 9, 10 you will have 4 bits. This will be the first 10 term in the sequence. The sequence has 1 1, 2 2s, 4 3s, 8 4s. So how many numbers are there is what they have counted. 2 number of 2s, 4 number of 3s. They say it will have 8 number of 4s because from 8 till 15 you will have 4 bits here. This is 2 power 1, this is 2 power 2 and this is 2 power 3. So when you have 5 bits, this will run for 2 power 4. It means for 16 numbers you will have 5 bits is what they say. They have given it in the form of general notation 2 power k minus 1. Now let's go for the next sum. The sequence where the nth term is the number of letters in the English word for the index n. The English word for 1 is ONE, which has 3 letters. So what is the first term here? You have to just calculate the number of letters. O, N, E will be 3. What about 2? T, W, O. What about 3? T, H, R, E, E. What about 4? F, O, U, R. So this is 3, this is 5, this is 4. So you have 3, 5, 4. Similarly for 10 you will have 3. So you are ending with 3. Next problem. Find at least 3 different sequences beginning with the terms 1, 2, 4 whose terms are generated by a simple formula or rule. The sequence should have 1, 2, 4 in the starting, but it should continue with other terms. They are asking us to find 3 different sequences with different rules. There are infinitely many possibilities for this particular solution. As for this explanation, I will take 3 possibilities. The first pattern, each term is twice the preceding term. A formula for this would be the nth term is 2 power n minus 1. So it can be 1 into 2, 2 into 2, 4 into 2, 8 into 2, 16 into 2, 32, it goes on. The next pattern, obtain the next term by adding increasing values to the previous term. We have 1 plus 1 which is equal to 2. Then 2 plus 2 which is equal to 4. We will have 4 plus 3 which is equal to 7. 7 plus 4 which is equal to 11. So this particular number is what they are saying as increasing value. So 1, 2, 4 is present here. 1, 2, 3, 4 is the increasing value they are saying to the previous term. So here the next set of numbers 11 plus 5 can be taken as 16. So this is another pattern 1, 2, 4, 7, 11, 16. The nth term could be obtained from the previous term by adding n minus 1. To move from the first term to the second, we add 1. To move from the second to the third, we add 2. Then we add 3. In this pattern, if we go, the sequence would be 1, 2, 4, 7, 11, 16, 22 and it goes on. So 16 plus 6 will give you 22. That's how they have taken the series. We are not restricting to only these 3 patterns. Again I am telling you, all your sequences should have the initial terms as 1, 2 and 4. Now let's go for the third pattern. Take n points on the unit circle and connect each of them to all the others by line segments. We will go with a pictorial representation. Take this as a circle. Take a point on the border of the circle anywhere. When n is equal to 1, there is 1 point on circle. How many regions are there for this circle? Only one region is there. We are taking the circle completely. So when n is equal to 1, we have 1 in the sequence. When n is equal to 2, we have 2 points. 1 point is here, 1 point is here. When 2 points are there, can we combine them with a line segment? Yes. So draw a line between them. Now how many regions? 2 regions are there. One in the top part and the other in the bottom part. So there are 2 regions. So this count of regions is what we are getting in the sequence. So when n is equal to 2, one line can be drawn making the circle as 2 regions. Now when n is equal to 3, this will be the third point. Do not erase the first 2 points and the previous line segment that we have already drawn. Sequence will be along with the previous terms you have to start. So now when n is equal to 3, are there 3 points? Yes. A triangle can be drawn. So already we have drawn one line. Along with that we are making it as a triangle. Now count the region. We have 1, 2, 3, 4. So the first 3 terms are 1, 2, 4. If we go in this pattern, we will get a different sequence. When n is equal to 4, this will be the 4th point. A square can be drawn. 1, 2 and already we have the triangle part. So square is drawn and 2 lines are drawn inside. So this particular line and already this line segment is present. How many regions are there? 1, 2, 3, 4, 5, 6, 7, 8 regions are there. So now we are adding 8 to this particular sequence. The sequence starts out like 1 to 4 but it goes with 8, 16, 31. This is when n is equal to 5 and this is when n is equal to 6. We have given a sequence namely 1, 2, 4, 8, 16, 32. This is one sequence. This is other sequence which is totally different. But here the initial 5 values are same as this sequence. So they have taken one more number in the sequence to tell that this is different from the first sequence. So this is the third sequence. Next problem. Let an is equal to 2 power n plus 5 into 3 power n for n is equal to 0, 1, 2. We are asked to find A0, A1, A2, A3 and A4. Let's take A0, 2 power 0 plus 5 into 3 power 0. So here n is equal to 0. 2 power 0 is 1, 3 power 0 is 1. So 5 into 1 will give you 5. This will be 6. So we have A0 is equal to 6. What about A1? N is equal to 1. 2 power 1 plus 5 into 3 power 1. 2 power 1 is 2, 3 power 1 is 3. 3 into 5 will give you 15. This is 17. A1 is equal to 17. What about A2? N is equal to 2. 2 power 2 plus 5 into 3 power 2. 4 plus 5 into 9. 3 square is 9. 5 nines are 45. This will give you 49. A2 will be 49. What about A3? 2 power 3 plus 5 into 3 power 3. This will be 8 plus 3 power 3 is 27. 27 into 5. 35, 10, 13. This will be 135. Overall this will give 143. So A3 will be 143. What about A is equal to 4? 2 power 4 plus 5 into 3 power 4. 16 plus 5 into 81. 3 power 4 is 81. So this will be 540, 405. Along with 16 will give 421. So A4 will be 421. Now let's go for a subdivision problem. Show that A2 is equal to 5 into A1 minus 6 into A0. So let's go for A2. What is 5 into A1 value? It is 17 minus 6 into A0 is 6 again. 85 minus 36 will give a value of 15. This will have 9. Then this will be 7, 49. Do we have 49 for A2? Yes. What about A3? 5 into A2. 5 into 49 minus 6 into A1 will be 17. So what is 49 into 5? It is 45, 20, 24. This will be 245 minus what is 17 into 6? It is 42 and we have 102. What is 245 minus 102? 5 minus 2 is 3, 4 minus 0 is 4, 2 minus 1 is 3. So we have 143 for A3. This is also fine. What about A4? We have 5A3. So 5 into 143 minus 6 into A2 is 49. So this will be 15, 20, 21, 715 minus what is 49 into 6? 9 6 are 54. 4 6 are 24 plus 5 will give 29. So this is 294. 715 minus 294. 5 minus 4 is 1. 11 minus 9 is 2. Then we have 6 minus 2 as 4. So ultimately we get 421. Did we get A4 is equal to 421? Yes, it is right. Now we have verified that A2 is equal to this value, A3 is equal to this value and A4 is equal to this particular value. All are right. Now let's get into the second subdivision problem. Show that AN is equal to 5 into AN minus 1 minus 6 into AN minus 2. So when you had 2 here, this is n minus 1 and this is n minus 2. When you had 3 here, it is n minus 1 and this is n minus 2. So the same pattern is also followed in A4 also. So now they are asking to show that AN is equal to this particular recurrence relation for all integers n with n greater than or equal to 2. So it is applicable only from A to keeping these two conditions as initial condition. Only then we will be able to compute using the previous terms. 5 into an minus 1 minus 6 into an minus 2 can be expressed as. So instead of an minus 1, 2 power n minus 1 plus 5 into 3 power n minus 1 minus 6 into 2 power n minus 2 plus 5 into 3 power n minus 2. 2 power n minus 1 can also be represented as 2 power n minus 2 into 2. So when you combine this 2 power n minus 2 plus 1, you will ultimately get 2 power n minus 1. So it can be expressed in this way. Similarly, 3 power n minus 1 can be expressed in this way. So what we are going to do is we are going to convert this power n minus 1 to power n minus 2. Only then we will be able to pick up the values outside. Let's keep 5 outside. 2 power n minus 1 can be represented as 2 into 2 to the power of n minus 2 plus we have 5 into already. So again we will have 5 into 3 to the power of n minus 1 can be expressed as 3 into 3 to the power of n minus 2. I am not keeping it as 2 power 1. Instead I am taking it as 2. Similarly, I am not keeping it as 3 power 1. I am taking it as 3. Minus 6 into 2 to the power of n minus 2 plus 5 into 3 to the power of n minus 2. So this is 5 into 2 which will give 10 plus 5 into 5 is 25. 25 into 3 is 75 into 3 to the power n minus 2. So I am multiplying these three terms and I am multiplying these two terms. So this is 5 into 2 which is 10. Then 5 into 5 is 25 into 3 it is 75. We will have minus here. We will have 6 into 2 to the power n minus 2. Then this minus will go inside. 6 into 5 is 30. So we will have 30 into 3 to the power n minus 2. So this 6 is multiplied to this particular 5 along with the minus. Now we have to take 2 to the power n minus 2 outside. So these two has to be taken out and these two has to be taken out. So 2 to the power n minus 2. We have 10 and minus 6 along with it. So we are bringing 10 minus 6 here. Now just go for 3 to the power n minus 2. Here we have 75 and here we have minus 30. We have taken it out. This is how we are bringing to this particular form. Now what is 10 minus 6? It is 4. What about 75 minus 30? 75 minus 30 is equal to 45. How can 45 be written? It can be written in the form of 9 into 5. So this is 9 into 5. 4 can be expressed as 2 power 2. 9 can be expressed as 3 power 2. When you have 2 to the power of n minus 2 into 2 power 2 together, this will become 2 to the power n minus 2 plus 2. Plus 2 and minus 2 will get cancelled and ultimately you will get 2 power n. Similarly, when you have 3 power n minus 2 into 3 square, this 2 will get cancelled and you will finally have 3 power n. So we are concluding with 2 power n after computing these two and 3 power n after concluding these two. This into 5 will stay as it is. What is this? 2 power n plus 5 into 3 power n. This is nothing but the an term. So we have proved an is equal to 5 into an minus 1 minus 6 into an minus 2. Next problem. Find the solution to each of these recurrence relations and initial conditions. They have asked us to use an iterative approach. In the iterative approach, we have to write an in terms of an minus 1. An minus 1 should be written in the form of an minus 2. Let's start with a problem. An is equal to 3 into the previous term and the initial condition is given as 2. So previously we saw 3 power n minus 1 can be expressed as 3 power n minus 2 into 3 power 1. Now we are going to do it for 3 power n. So this will be the previous term into 3 power 1. Let's start. an is equal to 3 into an minus 1. Now what is an minus 1? It will be 3 into an minus 2. Now keeping this 3 as it is, expand only an minus 1. So how many 3's are here? 2 3's are here. This can be combined as 3 square and we have an minus 2 here. Now this 3 square can be kept as it is and this an minus 2 can be expanded as 3 into an minus 3. So this will be an minus 2. Now how many 3's do you have? You have 3 3's. So 3 power 3 into an minus 3. When it is 3 power 3, it is an minus 3. Similarly, when you come till 3 power n, this will be the initial term a0. You have n minus 1, n minus 2, n minus 3 in this particular subscript. If you go in this way, what will be the final term? You will have n minus n ultimately. What is n minus n? It is a0. Similarly, we will have 3 power n minus 1 into 3. Which will give you 3 power n minus 1 plus 1. Automatically this will be 3 power n. This is what we are going to use. So this will become 3 power n ultimately. What is a0? It is given as 2. So this will be written as 3 power n into 2. So what is the solution of this particular recurrence relation? It is 2 into 3 power n. Solution means now when you apply n is equal to 0, 1, 2, 3, you will get the number in the sequence. Similar way we are going to solve b. an is equal to n into n minus 1 and the first initial term here is 5. That is a0 is equal to 5. Now let's start with an is equal to n into an minus 1. an is equal to n into an minus 1. So this n is repeated here. The previous term is coming to the subscript. Now if we have an minus 1, this n minus 1 will come here. It will become an minus 2. When we have an minus 2, this term will go here as n minus 2 into an minus 3. This n will stay as it is. This part is alone added here. Now you have to expand this particular part. So this will stay as it is from the previous problem and this particular part will be added here. If we go in the similar manner, what will happen is at one stage you will have n minus 1. N minus of n minus 1 means n minus n plus 1. You will have only 1 here. That is what is written in this particular form. And you will have a of n minus n. What is a of n minus n? This is equal to a0. Now rewriting this, we will have n into n minus 1 into n minus 2 into n minus 3 up to 1. So this particular part is taken as 1, a0. What is a0? It is 5. What is this actually? This is the factorial of n. What is factorial of n? We can express this as n into n minus 1 into n minus 2 up to 2 into 1. So this can be expressed as n factorial. So the solution to this particular recurrence relation will be 5 into n factorial. Next problem. Suppose that the number of bacteria in a colony triples every hour. So they have given two questions here. Set up a recurrence relation for the number of bacteria after n hours have elapsed. Since the number of bacteria triples every hour, the recurrence relation should say that the number of bacteria after n hours is 3 times the number of bacteria after n minus 1 hour. Let Bn denote the number of bacteria after n hours. This statement translates into the recurrence relation Bn is equal to 3 into Bn minus 1. This is after n minus 1 hours and this is the nth hour we can say. So 3 times into the previous hour. That's what we are expressing in this particular format. Now they have given a problem. If 100 bacteria are used to begin a new colony, how many bacteria will be in the colony in 10 hours? In 1 hour it will be multiplying 3 times. Now they are asking after 10 hours, how many bacteria will be there if initial bacteria count is given. The given statement is the initial condition B0 is equal to 100. The number of bacteria at the beginning is the number of bacteria after no hours have elapsed. We have to go with solving this particular recurrence relation. So let's get into the recurrence relation solution by iteration. Bn is equal to 3 into Bn minus 1. So now what is Bn minus 1? This will be 3 into Bn minus 2. This 3 along with this 3 will become 3 square Bn minus 2. Then for n minus 2 you will have 3 into Bn minus 3. Bn will be 3 power 3 Bn minus 3. This will go in the similar manner. So at one stage what you will have? 3 power n into Bn minus n. What is this n minus n? We have come to the initial condition. So Bn is given by 3 power n into B0. What is B0? It is 100. Now they have given 10 hours. 10 hours means the value of n is equal to 10. Let n is equal to 10 and we know that B0 is equal to 100. We have to substitute in this particular formula that we have got. So B10 is equal to 3 power 10 into B0. So 3 power 10 into 100. What is 3 power 10? This will give the value of 59049. Along with that you are multiplying 100 and bringing it to this particular count. So this is B10. Whenever we learn mathematics related concept, one thing that comes to our mind is where are we going to use it? So this will be one such application where you are using it. Next problem. For each of these list of integers, provide a simple formula or rule that generates the terms of an integer sequence that begins with the given list. Determine the next 3 terms of the sequence. Let's start with the first one. 10, 20, 40, 80. The terms in odd numbered positions are the successive powers of 2. 2 power 0, 2 power 1, 2 power 2, 2 power 3 and 2 power 4. The terms in even numbered locations are all 0. So what should be the next 3 terms? It should be 32. Then you should have a 0 here. Then you will have 64. This will be 2 power 5 and 2 power 6. So 32, 0, 64 will be the next 3 terms of the sequence. Now let's get into B. 15, 8, 1, minus 6, minus 13, minus 20, minus 27. The first term is 15 and each successive term is 7 less than its predecessor. So 15 minus 8 is 7, 8 minus 1 is 7. This is an arithmetic sequence and the nth term can be given as 22 minus 7 into n. We need not get into this particular sequence and all. We will just go with minus 27 minus 7 will give you minus 34. Minus 34 minus 7 will give you minus 41. Minus 41 minus 7 will give you minus 48. So here they have expressed in the form of an which is equal to 15 minus 7 into the previous term they have given. So 15 minus 7n minus into minus will become plus 7 here. So 7 into n and 7 into 1. This will be 22 minus 7n. And now the next 3 terms of the sequence can be calculated directly by subtracting 7 from the given last term. So minus 34, minus 41, minus 48. 1, 2, 3, 4, 5, 6, 7. If you take 8, 22 minus 7 into 8 will be 56. What is 56 minus 22? We will get 34. So it is minus 34. This is the 8th term, this is the 9th term and this is the 10th term. Even if you want, you can substitute 8, 9, 10 here and then find the value. Since it is minus 56, we are going with minus 34. The next problem, we have 2, 16, 54, 128, 250, 432 and 686. All these terms are even numbers. So if we divide by 2, we can obtain the sequence 1, 8, 27, 64, 125, 216, 343. What are these actually? N cube sequence. 1 cube, 2 cube, 3 cube, 4 cube, 5 cube and it goes on. This sequence is cubic sequence n cube. So the nth term can be 2 into n cube because after dividing it by 2 only you are getting this particular sequence. So when you are computing in this sequence, this into 2 should be taken here. So the an term is given by 2 into n cube. 1, 2, 3, 4, 5, 6, 7. you can find 8 cube, 9 cube, 10 cube and then multiply it with 2 in order to get the next 3 terms. Let's do for 1000. 1000 into 2 will give you 2000. So we know the final term is 2000 here. What is 8 cube? 8 into 8 is 64. 64 into 8 will be 512. So 512 into 2 will give you 1024. What about 9 cube? 81 into 9 will give 729. 729 into 2 will give 1458. So we have got all the 3 terms here. 512, 729 and 1000 will be the next 3 terms in cubic series. But this particular sequence is 2 into the cubic sequence. So we are going with 2 into n cube as the general rule here. With this we are completing this video. I'll meet you in the next video. Thank you viewers.